Hello friends, good morning, good afternoon and good evening to all. Myself Akshay Kumar, YA Chair, ASHRAE Chandigarh Chapter. Welcome to this webinar jointly organized by ASHRAE Chandigarh Chapter and ASHRAE Chennai Chapter. I am sure you all are aware about ASHRAE. ASHRAE is the American Society of Heating, Refrigerating and Air Conditioning Engineers. This society has been to serve humanity by advancing art and science of HVAC and R and their allied fields. This society consists all the professional members related to HVAC and building industry. With the initiation taken by ASHRAE Chandigarh chapter to spread knowledge among the members during the period of lockdown, today is our 18th webinar on experimental investigation of two-stage indirect or direct evaporative cooling system under different climatic conditions. To go through with activities done by ASHRAE Chandigarh chapter or any other region chapter. If you are ASHRAE member, then it's very good. If you are not, then be a part of ASHRAE by register yourself online at join.ashrae.org. Now moving on ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflict of interest. Now, I would like to introduce today's speaker, the ASHRAE Distinguished Lecturer, Professor Dr. Assam Aldin Khalil. Professor Dr. Assam Aldin Khalil is an Egyptian mechanical engineer. He's a professor in the Mechanical Power Department at Cairo University. He is the author and co-author of several international researches in HVAC field. He has many years of experience in delivering courses in air conditioning to university college students, to building managers and maintenance staff in both the industrial and commercial sectors in Egypt, the urban countries and worldwide. He has been selected by various universities and international organizations to lecture to graduate and postgraduate level engineers, managers, supervisors, and operating personnel on subjects of HVAC design and optimization, HVAC system management, energy utilization, waste heat recovery, plant management, and other related subjects. He is a ASME, AIAA, and ASHRAE Active Fellow, and is an ASHRAE Distinguished Lecturer. He is also the chairman of National HVAC Committee in Egypt, member of National Energy Code Committee of Egypt, and the chair of HVAC subgroup. He is registered HVAC consultant and the president of Arab Air Conditioning Code Committee. Now I want to do a small announcement. Recording of this webinar will be uploaded on our YouTube channel. Please subscribe our YouTube digital channel, ASHRAE Chandigarh. And the question answer will be done at the end of the session. You can ask your questions by typing in chat box, and same will be answered at the end by speaker. Now I request to Professor Khalil, please present your presentation. Now over to you, Khalil sir.
Okay. Well, very good afternoon. I'm very glad to have this opportunity to address you on the experimental investigation of direct and indirect evaporative cooling in various climatic conditions. So this research work has been done by some of my colleagues, Engineer Muhtadi Gawadi and Engineer Ahmed Shaban, under my supervision. I'd like also to acknowledge the technical support of Engineer Amin Higazi of Volta for this work. Now, I'll be talking about the fresh air for acceptable indoor and the cost of cooling of fresh air, indirect and direct evaporative air cooling, I will be speaking briefly about the experimental setup, error analysis, measurements, etc. Then I'll give a summary of the results obtained so far, and then discussion of these results, conclusions, and recommendations. So fresh air is one of the important parameters that we should have in buildings during ventilation, especially that not in every case we can use natural ventilation. The acceptable indoor air quality requires that the air should be clean and at temperature that provides thermal comfort. Examples of the fresh air that would be acceptable for indoor air quality in airports, shopping malls, stadium, workshops, like churches, synagogues, temples, etc. And in these applications, we expect to have a large number of audience, and consequently, as per ASHRAE, will have also very large amounts of fresh air requirements. And these, of course, are set up by the relevant standards, as we all know. So here, for example, extract from ASHRAE, ventilation for acceptable indoor air qualities, and it lists here that for every person, we need 7.5 liters per second to provide good comfort, thermal comfort conditions for a mall, for an example. So for a shopping mall of an area of 100,000 square meters, the required airflow rate will be enormous. And considering the weather in Cairo, for example, then we'll see that, and to achieve inside conditions or indoor conditions of 24 degrees centigrade and 50% relative humidity, and with outdoor conditions at this location, then you need cooling load of about almost 1,000 ton of refrigeration, which means that if you consider the cost, it will be horrendous. So shopping mall under normal condition work from 8 a.m. till midnight with 3,284 kilowatts of cooling. The load will be required about 1,000 kilowatts of power, electric power, 1 mega. Typically, if we use a water-cooled chiller and air handling units. Even at a low tariff of 1 Egyptian pound per kilowatt hour, the cost will be huge. By the way, $1 is about 16 Egyptian pounds. If we consider 16 hours of operation in such working conditions, then we pay about 1,000 Egyptian pounds, and this is way too much than it should be. Now, we have to think about another way. Thinking in another method, let's consider direct and indirect evaporative cooling, and that will be investigated in this particular work experimentally. So the purpose is to cool down the fresh air from the outdoor condition, whatever it is, down to room conditions. The main target will be Cairo conditions, in addition to selected locations around the world. By this way, we are trying to sort the problem of fresh air requirements in large enclosures. Here we have an example of the indirect evaporative cooling, where you have a heat exchanger and you have your primary air and secondary air in this facility, where you keep cooling this way. Or if you have the direct evaporative cooling by spraying water, and then you follow this process. And I guess that we all studied these two processes while we were in the third year mechanical. So now we are looking at the combination of indirect evaporative cooling and direct evaporative cooling. And in here we have tables where you have the day of the month the time and the weather conditions in any particular city. And in this case, we take the Cairo Airport weather station. By the way, in the Arab country, we have about 455 weather stations fully documented in large code. Now, if we look at this map that shows the variation of temperature, humidity, and climate conditions everywhere in the world, this is accumulated over the years, and it's dynamic, as per for reference in 2006, 2010, and 2017. And you can pick some of these zones to look at it and to be representative. So here we have selected 10 different zones around the world where we pick them to be different, and then we investigate them one by one to reach at what will be the most suitable, optimized method to cool down, to reduce the CFC or refrigerant cooling. For example, here, these are the zones from 1 to 10, equator, arid, warm temperature, and so the precipitation, however, fully humid, winter dry, hot dry, and so on. And these are the locations on the worldwide and the technical data of the altitude, latitude, etc. Now, the experimental setup was not laboratory type. No, it was a full industrial experiment performed in a company that manufactures already air handling units. And there was a direction to try to design a new section of direct and indirect evaporative cooling to reduce the energy and improve the energy efficiency ratio. So it is to remove the humidity is the problem in our computation. For example, you start by 40 degrees centigrade and relative humidity about 30, then you go down to 50% relative humidity, but temperature about 23 or 24 degrees centigrade. So we can do both of these in two different consecutive processes. First, we take the air, ambient air, and we cool it down in indirect evaporative cooling from stage 1 to stage 2. Then we do direct evaporative cooling from stage 2 to stage 3. At least now we have a cooled air, but at high relative humidity. Then we can cool down with mechanical refrigeration, but it will be at a lower enthalpy drop than if we use the normal conventional method. So we built direct evaporative cooling and indirect evaporative cooling sections. The direct evaporative cooling is we spray water into the air, and indirect we have a heat exchanger made of plastics or aluminium, where you can obtain effective cooling. In a sketch-wise, here you have the air, the hot ambient air, then you have the water spray in the direct way. Direct way, we spray water into the air directly, and as a result, we get cooler air, but moist. It has a higher content of humidity. So we have some disadvantages of the direct evaporative cooling, and it is not energy efficient alone. So we think about the indirect evaporative cooling, where we have surface in between, so they are not directly connecting each other, and we have our air coming and being subjected to heat transfer, and the other stream will transfer heat to it. So for the indirect evaporative cooling, we can have what we call regenerative, dew point, and also mesosthenic indirect. So to cut a long story short, that's the air handling unit, the conventional air handling unit, where you have the supply air coming from here, exhaust from the other side. And in this section, we have the other air that is crossing the main stream and exchanging heat through the heat exchanger in this location. Maybe if you look in detail, you'll see here in a plan that the primary air goes here, and because we are simulating all the temperature, humidity, and conditions of ambient air in different countries, then we need in this section to have a humidifier and to have an electric heater to control the temperature and humidity of the primary air. Then that follows into the heat exchanger section. Then you have here water spray, we have eliminators, and then you have your baffle, and then you have your pan to extract the air. So this is horizontally is my main primary air, while perpendicular to this stream, we have the secondary air, where we also have here at the end control of temperature and humidity. So you have a humidifier and we have electric heater. Naturally, you will have bell mouse venturi to measure the airflow rate here and here, and also gauges and sensors to measure temperatures and flow rates at every individual point. So the idea is to simulate the outdoor conditions in Cairo, Alexandria, Sharm el-Sheikh, Dubai, whatever, as an outside air here and also here. And then we spray water and use heat exchanger in order to cool down this air into conditions here. And then we compare the energy spent to cool down to the conventional method when we use mechanical refrigeration. In many cases, this type will not be enough, and we need additional mechanical ventilation, mechanical refrigeration. But at the end of the day, we are reducing the amount of energy we pay for, and a life cycle cost analysis proved that this system will be very successful. So let's go through the sections. Here we have the primary air simulator section, where you have the air coming in this way, and you have the electric heater, and you have the spray for the water to control the humidity. The heat exchanger section, which is an important element in the whole process, is made here of different materials. We thought of aluminium, plastics, and other materials. So this work is underway at the moment, and we are investigating the type of the packing, how it looks like, how it's been manufactured, because at the end we have to make it very cost effective. We have the water nozzle section, and here we are using 16 nozzles, 1, 2, 3, 4, 5, and so on. And these are coming from main manifold with a certain amount of water flow rate, and also the nozzles have a certain diameter which was optimized so the droplets will not be larger than needed or smaller. Smaller droplets means that we have a higher atomization pressure, which means higher pump, higher capacity pump, pressure pump, and so on, higher cost. So it's a matter of using locally available pumps that can do the job. Of course, to measure the airflow, we have a nozzle section embedded in the section, and we have the baffle eliminator. Of course, we have a humidifier section to control the humidity, and as you can see, these are plastic pipes arranged in this way. Also, we have tested the steam humidifier. So my two students who already obtained their master's degree had designed this steam humidifier with float control, where they can control the humidity of the air. Naturally, we have a control module, PLC, and the results come out to a laptop or computer where results are recorded. In order to do this process, we measure temperatures, thermocouples, flow rates by nozzle, and we have also wind anemometers to measure the air velocity, hygrometer to measure the humidity ratio, power, current to be measured electrically. So all the measurements were processed through computer, and in this methodology, both the inlet for the primary and secondary air are adjusted to outdoor summer air conditions in the city under investigation, whether it is Cairo, Sharm el-Sheikh, Dubai, any place in Dallas, or whatever. The selected air conditioning to be achieved in the primary by the primary and secondary air simulators. The data collected from the sensor is collected every 5 minutes. So we have a large number of data collection in order to raise the level of confidence in the results. For the primary set of measurements, the primary airflow rate was equal to about 1,000 cubic meters per hour. But at a later stage, I will be showing you before the end of my presentation that we already changed the primary air in 5 different settings with velocities, average velocities across the air handling unit inlet, varying from 0.7 meters per second up to about 2.5 meters per second, just to check the effect of the flow rate on the results obtained. The water is supplied to the secondary airstream in parallel flow setup at 3 different temperatures. Why? We thought the temperature of the water to be sprayed will be near the wet bulb temperature, which will vary. So we took it at 21 degrees centigrade, 23 degrees centigrade, and 25 degrees. We went even further, and we thought in sometimes, maybe if you have a chiller plant nearby, and we have some excess chill water, we can try at 12 degrees centigrade to use some of the water. So the water flow rate provided was 550 liters per hour. So the cities that we select in Egypt, we look at places where it is densely populated areas. Egypt is divided into 7 climatic zones: Alexandria, Aswan, Cairo, Sharm el-Sheikh, Barafra, Minya, and Luxor. And if we put them on a map, that's the map of Egypt. And these are the climatic zones as proposed by Khalil and Medhat in 2005. So we have 7 zones. Each of them has a different characteristics. And to make a long story short, we like to provide in these different zones the energy efficiency ratio for direct and indirect evaporative cooling, to tell our clients or to tell people at large where is best to use which method. So the parts I'm going to speak about now, these are some of the nomenclature and definitions. Primary air temperature, dry bulb. Primary air outlet temperature, dry bulb. Primary air inlet water temperature. Inlet water temperature, that's for the spray. ETA is the wet bulb efficiency. EER is the energy efficiency ratio with the international definition that we all know. CC is the cooling capacity. ER is the energy reduction. Q is the flow rate, and RH is naturally the relative humidity. Now, in order to compare the experimental results, then we look at the 3 different terms and definitions. EER, which is the energy efficiency ratio, that's the cooling capacity per ton divided, the cooling capacity divided by the power, which is the coefficient performance. And we have also the effectiveness and the temperature difference. So if we look for the indirect evaporative cooling in different locations, and you see at 21 degrees centigrade, 23 degrees centigrade, and 25 degrees centigrade, these are the difference in temperature of the primary air coming in and out. So in Sharm el-Sheikh, when using indirect evaporative cooling, we can gain 20 temperature, 20 degrees centigrade difference if we use water at 21 degree spray. While in Alex, this difference is less, naturally, because the air here is more humid. So its capacity to carry more water is less. While in Aswan, which is a little bit dry, you have the capacity to, with using indirect evaporative cooling, of temperature difference of 22 degrees centigrade. That's the difference between the primary air inlet and the primary air outlet. If we go further, that's in June. And here also in different cities. In August, and so on. And that's all by simulating and doing measurements, repeating the measurements, typically 100 times until we have a steady state condition. Here in August, and also here in June, but in Alex. So these are the effectiveness. At different cities. So the effectiveness is more than 100% in different cities. You may ask me how sure the results are to be repeated. We repeated the results at different times for the certain locations, and it is repeated within plus or minus 0.5%. For example, here, that's the energy efficiency ratio. So if I have a I have an evaporative cooling system in this zone, the energy efficiency ratio will be 19.5. Well, you know that any mechanical refrigeration system will have an EAR of 14, 20, 15, 11, 12. But here, because we are using less mechanical, then we are putting less energy to obtain the same coolness or cooling capacity, then the energy efficiency ratio is higher. As you can see, it varies from zone 1, where they have 13.7, to zone 2, which have 16.9, zone 7, which have 19.4, because here we have it about 17.8, and in the south, where it's very dry, we have 22. If we use water temperature of 23, we expect to have less energy efficiency. Why? Because the water we spray is at a little bit higher temperature, while in the previous one, the water we sprayed was at 21 degrees centigrade. So naturally, in this case, we have higher energy efficiency ratio, while in here, the energy efficiency ratio is reduced. For example, here at 21, the energy efficiency ratio is 19.6. Fine, very good. But if we go to 23 degrees centigrade water spray temperature, then the ER is 17.7, still higher than the conventional value. So I'm just trying to walk you through the results. I'm not going to bore you with more experimental results, but once you get the test rig calibrated, tuned and running, you expect to get multiple good results that can mean a lot to the designer. Now let us go to 25. 25 still, the ER is higher, but less than at 21 degrees centigrade spray water temperature. So in total, we reduce the energy that we purchase, we reduce the carbon footprint, and we use less conventional fuel. Of course, that incur cost. It's the cost of the extra pumps, the cost of the heat exchanger, and the cost of the sections themselves. So we did also run this life cycle cost analysis in order to better know the feasibility of the proposed solution. Now, we also tried, when we have the water spray at 12 degrees centigrade. and we say 12 degrees centigrade is the temperature that we can get from chilled water in this case. So here you can see that we have energy efficiency ratio of 27.3. Wow, that's a lot. But of course, you are considering the cost of producing 12 degrees centigrade. Now, as I promised you, I will be speaking about the effect of the airflow rate. So instead of having flow rate of 0.7 meters per second average velocity, we raised the air coming to the section 1.5 meter per second. And here in August, we see that the energy efficiency ratio increased. Then we increased it further to 2.5 meter per second. 2.5 meter per second is the classical design air velocity that we use when we are doing air handling units. And here we have a further increase in the amount of energy that we save. We are still at the beginning of our investigations. Currently, we are doing different designs of heat exchangers, different material, different nozzle diameters, but in all cases, we are focusing on recommending equipment and material that are locally available, that are not expensive, that will be cost effective. Because at the end of the day, we are going to design and manufacture an additional section to the air handling unit that will reduce the energy consumption by increasing the energy efficiency ratio and so on, reducing the carbon that is being used. I'd like to conclude the indirect evaporative cooling and direct evaporative cooling is a useful cooling process for many situations, but it depends on the control system for optimized operation, especially in high humidity operations. Cooling of fresh air using direct evaporative cooling may be enough in some situations to remove the entire cooling. What about if we design an air handling unit to reduce the outdoor air coming into the unit, the fresh, down to 26 degrees centigrade and humidity of 50%. In this case, I will not need any additional cooling. It will be okay. And it will be okay for locations where we have masses, we have large population of people, like in malls and places of assembly. Further enhancement can be achieved using the air-to-air heat exchanger to cool the fresh air using exhaust air from a building. That can be done. Another enhancement may be achieved using direct evaporative cooling system for exhaust air after passing through air-to-air heat exchanger, as mentioned here. It was beyond the scope of this work to study the effect of using chilled water in the operation, but principally it will provide better conditions. So for our future work, with these recommendations, we are doing financial investigations to look into the savings in both of the capital and running cost of the system, because because we have the pumps for the sprayed water, and we have also for the humidifiers. We have the energy for the humidifiers, and we have the power for the fans, and all these has to be considered in your life cycle cost analysis. Testing different material that can be used for the indirect evaporative cooling is very important. We have to look into the heat transfer capabilities and also the financial feasibility of using these systems. I'd like to thank you for your patience, and I'll be ready to entertain any questions if you like. Thank you very much.
Thank you, clear sir. Thank you. This was very interesting presentation. You had very well explained what indirect evaporative cooling and direct evaporative cooling. Now we are almost ending of this webinar. Before ending of this webinar, we will take a few question answer. Audience has raised their questions in our chat control panel. So I will read that questions, and you have to answer for these questions. Now, first question is asked by Mr. Jati Vidiputra. He want to ask how much set point for RH, and which one more efficient, direct or indirect cooling system?
Thank you very much. A very good question. The direct evaporative cooling is very useful, but the indirect evaporative cooling is more effective in this case.
Thank you, sir. Another question from Mr. Deepak. He want to ask, what is meso-synco cycle for indirect evaporative cooling?
It is one of the methods used for the evaporative cooling. You mean this one, where you look for the size of the particles or the droplets in your indirect evaporative cooling.
Okay. So another question from Mayank Dubey. We want to ask, should we also include the energy required to cool the inlet water to 21 degrees Celsius or 23 degrees Celsius or 25 degrees Celsius in the EER or COP calculations?
Of course, but the water is the water is the natural water from the river is considered to be at 21 or 22 or 23 or 25. So actually, if you take any underground water or river water, then that's the temperature. So you are not cooling it. But of course, if we use the chilled water at 12, of course, this is included.
Another question from Muhammad Abole. They want to ask, what about water consumption and the outlet water temperature?
The water temperature? Where?
They just want.
We use the water.
Yes.
We use the water from the mains at 21 degrees centigrade, or 23 centigrade, or 25 degrees centigrade. So these are the mains water, the city water. We do not cool them down. We do not heat them up. So our suggestion is the water you spray to the system will be the city water. Of course, it has to be of certain quality, total dissolved salts to be less than 500. So we are using about potable water in order not to clog the nozzles. And because the smaller the nozzles, the more difficult the handling because of the pressure drop across the nozzle.
Okay, sir. Another question from Vivek Balero. He want to ask what is the lowest low temperature difference in primary air temperature with reference to the secondary air temperature, indicating the efficiency of the heat exchanger.
What is the lower?
Lowest temperature difference in primary air temperature with reference to the secondary air temperature, that indicating the efficiency of heat exchanger.
The primary air inlet temperature and the secondary air temperature are the same because they simulate the reality in the city we are studying. So the primary air is the air that's going to go to the system, while the secondary air is the air also going to cool down the primary air by evaporative cooling. So both of them are at the same temperature, which is what we call ambient temperature.
So now last question of this session by Arun Cheria. He want to ask, there is a concern about corrosion of internal components like fan section and internal walls of such system. Any specific things in a design has to keep in mind while specifying such system?
You mean the design of the fan?
Yes.
Well,
Design of
the only concern is that because, well, the fan comes at the end of the line, so already it will be a normal. The water is already being eliminated by the eliminator, so I don't expect to have an effect on this. But of course, it has to be corrosion free. But that's normal, what we usually do for an air handling unit. I cannot see any special requirement for the air handling unit. Actually, we are using a normal air handling unit, and we're adding a section to provide this evaporative indirect and direct cooling.
So now one more question received from Mehak Dumpe. This is now last. With increasing air velocity, does the EER continue to increase always? Do you expect
Yes.
the EER would reach a ceiling and would not improve any further after an optimum value of air velocity?
No, the EER will not increase continuously because you are not allowed to increase the air velocity into the primary air section. Otherwise, you'll have noise. So you have restrictions of velocity of the air. But if you maximize the amount of evaporative cooling, then of course you reduce the energy component that you buy by mechanical refrigeration.
Thank you, sir. Thank you, sir, for this presentation. And I also request all the audience who have raised more questions on later on stage. We will answer your questions on later on stage. You can raise your question and at our email ID ashrae.chd@gmail.com. At the later on stage, we will answer your all the queries. And
And
now,
I can make my presentation available to everyone.
okay, thank you, sir, for this. Uh, Now, thank you all for your participation today. We are so grateful for your support. Without you, this would not be possible. I also thank you all our ASHRAE Chandigarh team and ASHRAE Chennai chapter team who supporting us in this webinar. This is a very interesting webinar. Sir, you had very well explained about indirect evaporative cooling and direct evaporative cooling. So now again, thank you, audience. For Now, I want to announce our next webinar, which will be held on 26 May 2020 at 6:30 p.m. The topic for next webinar will be Fundamentals of ASHRAE Standard 55. The speaker for this program is Mr. Robert Bean. He is also a ASHRAE DL. We will see you there. And this is our YouTube channel. This recording of this webinar will be uploaded on our YouTube channel. Please subscribe our YouTube channel for the latest videos and all the webinars done by ASHRAE Chandigarh. You can see all the videos. This is our upcoming webinar list. So next webinar on 26th May, after then 30th May, 6th June, and 20th June. Now, stay safe and stay connected with ASHRAE. Thank you, everyone. Thank you. Now, over to you, Osama-san.